in this afternoon session, we will also review the status and the outlook for the deployment of a hydrogen infrastructure in South Australia. So without further ado, I will start by introducing our first speaker, Mr. Greg Peen. Greg, he is an executive director of the Energy Management Institute in the College of Business at the University of Houston. In his position, he is responsible for energy education, research, events, and industry outreach. At the college, he is also a faculty director of the Master of Science in Global Energy Management degree program as an adjunct faculty member. His research teaching experience is for 40 years. His focus is more into the transition to a sustainable energy system. Greg, floor is yours, please, and thank you.
Great. Thank you, everyone. Good day, I will say. We're somewhere between morning and evening, I think. I wanted to provide a bit of an overview on kind of hydrogen's potential role in the energy transition. As you think about the infrastructure, I think it's helpful to think about the broad scope that might be required. And so I will try to cover that. First of all, and just starting with kind of one of my favorite quotes about hydrogen, which comes from Jules Verne about almost 150 years ago, where in one of his novels, he talked about his belief that water would one day be employed as a fuel, that hydrogen and oxygen, which constituted used together singularly, would furnish an inexhaustible source of heat and light. So that I think kind of sets up some thinking that was done nearly 150 years ago, which is now suddenly becoming relevant today. Perhaps if I could ask if the mic in the room could be muted. Great, thank you very much. So first of all, what it is about hydrogen that really drives our interest? It's obviously a very unique element. Its combustion process is very clean. It produces only heat and water. It has a very high specific energy content, 3 times the energy content of gasoline by weight. And that really drives our key interest in hydrogen, which is its value as an energy carrier in parallel with electricity, and also as a storage medium. Of course, one of the great things about hydrogen is it can be produced by electrical energy and vice versa. We can produce hydrogen by electrolysis, converting water and electricity to hydrogen. And then we can also convert hydrogen and oxygen to electricity via fuel cells. So our interest in hydrogen has been... I'm sorry, is it possible to mute the mic in the room? It's been traditionally limited because of its very high cost of production, but now with interest in sustainability and climate change, we've come to focus on what role that hydrogen could play. And so in terms of an overall role in a low or zero carbon energy world, we can talk about the full value chain for sources of hydrogen, whether they're zero carbon or so-called green pathways, or whether we're talking about blue hydrogen production, which is from fossil fuels with carbon capture, energy storage and transportation, very important. Hydrogen can be moved and stored in a number of different ways, the different physical forms of hydrogen, as well as the different hydrogen-derived energy carriers like ammonia, methanol, etc. And one of the key important aspects of hydrogen is its potential role in long-term energy storage. One of the beauties of fossil fuels are that they are very energy dense and they are easy to store and move around the place. And in fact, if you add it up, about 15 to 20% of global energy demand is currently held in storage in the form of fossil fuels as the primary energy system buffer. So as we move away from fossil fuels, we need other methods to be able to transport and store hydrogen. And then, of course, we need to think about the back end of the value chain, the different zero carbon energy uses. Part of the infrastructure has to be the introduction of devices that will use hydrogen in the various sectors, whether that's transportation, potentially residential, commercial, industrial applications, particularly those around high heat and some of the heavy energy intensive industries, as well as a potential role in power generation. Obviously, the future role of hydrogen is somewhat uncertain, so it can be helpful to think about that in terms of scenarios. This is the IEA's net zero scenario, where they project an increase in hydrogen production of about 5x over the next 30 years, with significant penetration in transportation and industry, as you see here on the right, both in transportation in terms of shipping, heavy-duty road transport, aviation, and then in industry, especially in chemicals and iron and steel. We're going to need some technology development. The good news is that a lot of the hydrogen-related technologies that we need have been around in early forms for many years. We list some of these here, things like electrolyzers, fuel cells, and even PV cells for solar power for the electrolyzers. So while these technologies have been around for a while, they have not been really developed and applied at scale, which is the task that we have before us. So if you think about all of the technologies that we would need and all the infrastructure that we would need to have a complete global low carbon or zero carbon hydrogen value chain, that's what this chart is trying to illustrate. This comes from the IEA and some of their work on looking at the maturity of all the different technologies that we might need. So you go from blue and green, which are technologies that are either mature or in adoption phase, to the lighter colors, where we need more work being done. And you can see going on the value chain from left to right in terms of production, infrastructure, and then the different aspects, the different investments that we need and the different technologies that we need in terms of the various potential uses of hydrogen. When we talk about hydrogen, people tend to talk about different colors of hydrogen, gray, blue, or green, but I think increasingly people are going to focus much more on the carbon intensity of the hydrogen. How many kilograms of CO2 equivalent are incurred to produce a kilogram of hydrogen. There's been a lot of development and a lot of thinking about how cost might evolve. And this is some interesting analysis that was done recently, which suggests that as we move over the next 20 to 30 years to large scale adoption of green hydrogen produced by electrolyzers, that the capital cost and hence the implied cost of the hydrogen could drop very dramatically from $4 or $5 a kilogram today to potentially $1 a kilogram or even less with very large adoption. When we think about the demand for hydrogen, there is potential demand in all of the end use segments, but hydrogen will probably find its best markets and penetrate more highly in the more centralized applications where it will have some advantage versus electricity. When we think about the new low carbon, zero carbon world where we're moving from the use of fossil fuels to primarily electricity and energy use, which is either through electrification or hydrogen, we then kind of need to look at, well, which solution is likely to be best. And as we can see here, the focus on, for hydrogen, some of the transport sectors as well as the industrial sectors. And we see probably less use in buildings and in light-duty transportation, particularly light-duty transportation, where the relatively lower efficiency of well-to-wheels of hydrogen versus electricity and battery electric vehicles mean that probably won't be too much penetration there, but where we will see the penetration, where we will need the infrastructure, is in the heavy-duty transportation subsectors, whether that's heavy-duty trucks, shipping, aviation, which is probably the single biggest challenge that we have given the energy requirements and weight restrictions associated with fueling aviation, as well as in the hard to abate industrial sectors. So we've got production of hydrogen, we've got demand in different sectors, and we expect that hydrogen trade will evolve, and that regions that have low potential hydrogen costs and small populations and potentially small demand centers will be in a position to export, and depending on their renewable energy resources, be they solar or wind, would be in a position to export hydrogen to countries that will be short of renewable energy capacity. And this is an initial estimate that IRENA has done earlier this year on where the exporting regions might lie, where the importing regions might lie, and where other aspects might be somewhere in the middle. And it's very early days to be estimating not only supply demand, but then obviously trade between importers and exporters. But this is a first pass at seeing how an international trade regime might evolve for hydrogen. When we talk about hydrogen and its role as an energy carrier, it's important to think about the fact that there are a lot of different ways that we can use hydrogen or hydrogen-derived compounds as energy carriers and storage mediums. Some of the big ones are liquefaction of hydrogen, hydrogenation of liquid organic hydrogen carriers, or ammonia. All three of these are potentially available for long-distance transportation of hydrogen energy. They each have different advantages and challenges, as you can see here. And obviously the cost will influence the cost of delivery of hydrogen from an importing environment or from an exporting environment to an importer would vary by the choice of carrier and transportation mode. And you can see here, these are some estimates for different pipelines and different types of hydrogen carrier tankers, and what the estimated cost would be in dollars per kilogram on the y-axis compared to the distance traveled. One of the important things to think about in terms of hydrogen-based energy carriers and which one will make the most sense in different applications is what is the energy available after transportation and conversion. So when we start with the energy consumption of the hydrogen or the hydrogen carrier at the production source, we then have to take into account the energy consumption used for conversion, for shipping, and for potentially for reconversion. And you can see here what some of the penalties are for the different hydrogen carriers. And this is done on a kind of pro forma, assuming an 8,000 kilometer shipping distance. So you can see energy consumption in the various aspects of moving the hydrogen or the hydrogen carrier along from production source to demand center. The energy conversion losses are very important. A lot of companies, this is an example of projections by Shell, believe that the cost of the integrated value chains will drop significantly to the point where you will be able to have delivered hydrogen. And I think this is an example from Australia to North Asia, I think Japan, of their estimates, and this is a couple of years old, of the cost, delivered cost of hydrogen below $4 a kilogram, which would be quite a significant reduction from where we are today. I think it's important when we talk about hydrogen to remember that we can also include green ammonia in that process. So starting with zero carbon hydrogen, which is produced by electrolysis, we can then take that hydrogen and use it, and using the traditional Haber-Bosch ammonia production process with nitrogen from air separation, we can create so-called green ammonia, which can be a very effective hydrogen energy carrier, but it can, and what's interesting about ammonia is it can be used in many applications directly. It doesn't necessarily, you don't necessarily have to crack it to extract the hydrogen back out of it. At the end of, when we get to the end use location, in many cases, we can actually use the ammonia directly as an energy source. This is just a little bit of background on a couple of the sub-markets. This is the IEA's Net Zero 2050 scenario, and their assessment of what the marine market might look like. And as you can see here, whether it's in the form of ammonia or hydrogen down at the bottom, they're projecting that hydrogen-derived fuels would have a significant market share in the shipping industry. There's also the possibility of producing synthetic hydrocarbons from green or blue hydrogen and captured CO2. However, this is likely to remain a very expensive way to produce synthetic hydrocarbons, and is probably likely to be limited pretty much to aviation fuels. You can see here the kind of technology readiness of the associated components of a synthetic fuel, jet fuel value chain. And then you can see here the IEA's projection in Net Zero 2050 that synthetic hydrogen-based fuels, those are synthetic jet fuels produced from green hydrogen and captured CO2, would have about a third of the aviation market, with a lot of the rest of it being done by drop-in advanced biofuels, and then with a small amount of petroleum-derived aviation fuels remaining even in 2050. Then finally, in addition to ammonia and synthetic liquid hydrocarbons, we want to talk about methanol as an energy carrier. Methanol is currently produced very broadly around the world and moved around the world primarily as a chemical feedstock, but it also does have fuel uses, particularly in China. And methanol is potentially a green energy carrier where we produce it from captured CO2 and green hydrogen. Methanol is interesting, particularly for a lot of the shipping people, because it has the highest volumetric energy density of any of the hydrogen-derived compounds. And you can see here, of course, the challenge in terms of trying to replicate the liquid fossil fuel volumetric energy densities with the various hydrogen-derived energy densities. But to make truly green methanol, we need biomass-derived CO2 and green hydrogen. So it's a more complicated operation to produce truly green methanol. And that's basically to offset the CO2 that is produced when the methanol is burned, or unlike burning either pure hydrogen or ammonia, where those are that's carbon-free combustion. So again, this is something that is of interest to a number of shipping companies who are trying to figure out if they can create a kind of integrated biomass methanol value chain. So again, in summary, hydrogen could play a large role, potentially 15 to 20% of energy demand. we would have to have a significant increase in production, a lot of technology development, but there's a lot of optionality with hydrogen in terms of how it's produced, how we convert hydrogen to different energy carriers, and it has a significant role in a number of end-use demand segments, particularly some of the heavy transportation segments, and a hard-to-abate industrial segments. So I'll stop there.
So our second speaker is Mr. Wolfgang Brand. Mr. Brand, he's the Vice President of NEOM Green Hydrogen. He is responsible for developing and implementing the world's largest green ammonia project. Mr. Brand joined Air Products in 2020, bringing 20 years of experience. Before Air Products, he was the Chief Executive Officer and Managing Director of ENT in Pittsburgh, Germany. So welcome, Mr. Brand. Please proceed with your presentation.
Good afternoon, everybody. Good morning. The distinguished guests and other speakers, thank you very much for giving me this opportunity to talk about the building hydrogen infrastructure. I was a little bit worried to speak after Greg, being an authority in that field, but I find that, Greg, thank you very much. You perfectly staged what I'm going to tell you, because a lot of things that Greg outlined in that whole portfolio of possibilities that is now happening in the future, I will just add what we are now already doing in the industry and how we are going to make it happen. A very quick word on Air Products. Air Products is one of the largest chemical companies in the world, industrial gas-based company. We just have the same market cap as SABIC, so that you just have an idea of the size of our company. So we are one of the big industry companies, and we are determined to make the energy transition happen. Like Greg outlined before, this is a transition from fossil fuels-based energy systems into a new world of renewable energy. And yes, there will be a lot of direct use of electricity, and this is good, and the world needs that, but there will be elements that can't be directly electrified, and then we need another means of energy carrier, and hydrogen is the most promising energy carrier that we have today, in particular for the segments of transportation, heavy buses, trucks, trains, ships, airplanes, and the heavy industry that needs a lot of energy, where hydrogen would be the solution. The whole journey is a transition, so it will not happen overnight. It will happen in different speeds and different geography, but we are absolutely convinced that the world has decided to stop burning fossil fuels. In 20 years, in 30 years, in 40 years, this is not going to happen in any region in the world anymore. And this is why we need to do what we are starting to do now to change the world's energy system. Greg, I really liked how you formulated that at that point, that we are having this for colors of hydrogen, gray, blue, green, and other colors in the game. But at the end of the day, we had different shades of gray, and we now have different shades of blue and green. So we are better talking in an academic environment about the carbon-intense hydrogen and the low-carbon hydrogen. So the traditional hydrogen, as we have it today, is coming from fossil fuel-based systems, and there's of course the classic steam methane reforming or the ATR process, but there's also gasification, which already is an enhancement when you look at what it does in the overall use of energy, because we are using something that is the low bottom of the energy at this moment. It's coal that can't be used, or it's even residual oils, and that will be gasified into hydrogen, a clean mean of energy at the end use. It's still gray, it's carbon-intense hydrogen, but it's already a step forward. Blue, as Greg explained, is producing hydrogen with carbon capture and not releasing carbon dioxide to the environment, and green would be producing or is producing hydrogen from renewable energy sources. Gray is what we have today. So today we have already a hydrogen system, and it's largely used in pockets in the industry, of course, not as a broad energy carrier. But that's starting to change, because the hydrogen business is picking up, and we will also going forward need gray hydrogen. Will it be there in 30 years, 40 years? I can't tell you the future, But for now, we will have an important share of gray hydrogen. And this is where Air Products is in total capacity #1 in the world. We have over 110 hydrogen production facilities around the world, and we produce over 8,000 metric tons per day hydrogen all over the world. This, of course, will now change dramatically when we add more and more capacity, in particular in the field of green and blue. And this brings me to the next stage, to tomorrow. And tomorrow starts really tomorrow, not in 10 years, not in 20 years. For Air Products, it starts tomorrow. We are already working on heavily on a few projects in that blue area. This is when you produce hydrogen and sequestrate the CO2, so you don't emit greenhouse gases, in particular CO2. And a very good example of that is the project that we are doing in Canada. So we have announced that project, and that project is in full swing and execution. We are producing a net zero energy complex, including an ATR, an autothermal reformer, to convert natural gas into hydrogen. We have more than 95% carbon capture in the process. Now you may ask, why the net zero? I will explain on the next slide why technically we are net zero, even if we have some carbon dioxide still leaving the plant at that point. We are having a liquid hydrogen plant connected to it and existing to a pipeline, connecting to an existing pipeline system. The total capital that we invest is around the 1.6 billion Canadian dollar, and we will be on stream by 2024. Here's a schematic of what we do here in Alberta. So reading from left to right, you enter this flow chart with natural gas into the process plant, the ATR, and that ATR is emitting some carbon dioxide. So why now net zero? Because when we produce the hydrogen, we use some of the hydrogen to not only power our plant, but also export power. And that exported power is replacing gray power in the industry and in the communities, which would emit carbon dioxide. So all in all, if you do the balance around our plant, we are helping to have a negative impact on CO2 after we have produced our hydrogen and exported the power. On the right side, you see the customer side of the infrastructure, and I like that, how this webinar is set up, that we are talking about the infrastructure. We're not talking about, hey, we need a big hydrogen plant, because it's so much more. So people that I read a lot of announcements about green hydrogen in particular, where people are developing individual standalone projects. This is not doing the job. We have to connect it to the customer base. We have to develop the customer base, because today there's not many customers that directly need a lot of hydrogen. Only with availability of infrastructure, that customer base will automatically grow, because we have to turn away from the fossil fuel-based energy system. So in Alberta, we have a pipeline and we have a liquefier to transport liquid hydrogen for the merchant market and to our fueling stations for hydrogen for mobility. We have another good example, also recently announced in Louisiana. In Louisiana, we are building a very large natural gas-based hydrogen production plant that is also completely sequestrating the carbon dioxide. So that is blue hydrogen in terms of color. We are producing 750 million SCFD blue hydrogen and have an ammonia plant where we can either support the hydrogen for the local business, including a 700-mile long hydrogen pipeline that already exists and Air Products owns and operates. And we can produce ammonia, and with that ammonia we can, of course, like we heard from Greg, transport over vast distances. That's the beautiful thing with ammonia, that it doesn't really matter if it's short or long. We can transport it to global markets. The pipeline is instrumental. We are talking about hydrogen infrastructure. So with a pipeline, you're transporting molecules, and molecules by definition are color agnostic. They are not green, they are not blue, they are hydrogen. So it's all about getting it right in the terms of certification. When you produce blue, when you produce green, that the customer can rely on a system that is not cheating, a system that is reducing the carbon footprint more and more until we are completely at net zero. But a hydrogen pipeline like hydrogen storage, is instrumental in doing that mass balancing around that color game, in particular in the transition phase. Now coming to the thing that is dear to my heart, the last 2.5 years, I have developed and started to implement now the NEOM Green Hydrogen project. This is an exciting journey. A lot of people are talking about green hydrogen and think of it as like putting an electrolyzer somewhere and producing hydrogen. And this is technically true, of course. The thing that you need is renewable power and an electrolyzer, and then you have green hydrogen. But to really develop the infrastructure for green hydrogen is something way beyond that simple. So looking at the NEOM program is a simplified flowchart here. We're delivering this carbon-free hydrogen, and this is really truly carbon-free because we will build our own power plants in NEOM. So together with NEOM and ACWA Power, we have a joint venture company, NEOM Green Hydrogen Company, that is now building this infrastructure. And the wind and solar will be one of the largest wind and solar fields that are built as a single phase. We have announced a total power of 4 gigawatt, which is, I think, the power that a state like Denmark is operating on. And with that power, our own island private network power, we go into a large electrolyzer, which definitely will be the largest electrolyzer built at that time with more than 2 gigawatt. ThyssenKrupp is a selected technology company that is supplying the electrolyzer. Producing hydrogen, green hydrogen, no carbon footprint at that moment. We are also powering our air separation unit with green power, no carbon footprint at that process step. We produce nitrogen. Like we heard from Greg, hydrogen and nitrogen in the Haber-Bosch process goes to ammonia production, again powered by renewable power. So this is also carbon-free ammonia. Then Air Products, the global company, is the sole off-taker of each and every ammonia molecule produced by NEOM Green Hydrogen Company, and we will ship it. And I have more slides to explain where we are going. The shipping, of course, at this moment in time is also in the transition. So we have had announcement that there is ammonia ships tested and built. That, of course, looks like to be a perfect solution. But initially, there will not be a 100% fleet of ammonia-powered ships. So we also will have transportation by classic ships, which will add some carbon footprint. Here, scale really matters, because if you do that on a small scale, you add a lot of carbon footprint to your molecules. If you transport with very large ships, then this is an acceptable dilution of being carbon-free, but it's still low carbon in terms of all definitions that the world is using at the moment. Then when we arrive at the port, Air Products will build a couple of port projects. We have recently announced them, and I will show them. And we will go into an ammonia dissociation process, the reverse of the Haber-Bosch in principle, a catalytic process. Air Products has developed their own technology for this, and we will convert it back to hydrogen and then put it in compression and or liquefaction to supply to the market, very similar to what we've seen before on the Alberta and Louisiana project. Also worth mentioning, a small footnote here, NEOM is also developing a Hydrogen Innovation Development Center, HIDC, and the NEOM Green Hydrogen Company with Air Products is supplying the Element 1 electrolyzer, which will be in operation already next year. So we have a lot that we can demonstrate and learn already during that period until we are delivering the full project. Just in numbers, the project is stunning. So we have announced that the project costs more than 5 billion. We have 5 significant key contracts to manage that are all above $500 million US. The plot area, process solar and wind in particular, of course, the wind farm is vast. It's 400 square meters. And that's all of them. We're talking about building a hydrogen infrastructure. How many NEOM's green hydrogen projects will the world need? Many, many. And look at that numbers. So this will be a challenge for the world to build enough wind and solar. We expect on our project more than 10,000 labor in peak with 41 million work hours at site, also coming with all their safety challenges to deliver that safely without any lost time incident. We have more than 3 million hours on engineering and 3.5 million hours to supervise the sites. Our sites are not all at the same place. We are all in the NEOM region, but they are connecting between the wind farm, the solar farm, and the process plant with distances more than 150 kilometers with overhead traveling lines. A lot of engineering documents, steel and concrete, of course. The project is developed as a financing project and has a joint venture setup I explained before. On the downstream side, so receiving the green ammonia, we are shipping to Europe, United States, and Asia. And a typical port project always looks like a Lego system. You have different building blocks. So you have what is shown purple here. You always have to have marine facilities and ammonia storage, because we need to offload the ammonia and need to store it for continuous processing. And then, of course, there may be the option to transport ammonia, like with trailers or barges, into other hubs in that region. Or we go and continue into processing with what is shown here as ammonia cracker, the dissociation process to convert ammonia back to hydrogen. And then, like as I explained before, you either go to a pipeline, you compress it to a high pressure hydrogen, or you put it directly to the customer with a refueling station, or you liquefy it if you have like the mid-distance transport. NEOM is really happening, not only the generation plant in Saudi and waiting for customers. NEOM is happening on the low carbon hydrogen for air products for the world. We have announced already 3 terminals in Europe. We have announced Immingham ammonia terminal in UK. We have announced Rotterdam ammonia terminal in Netherlands, and we just a week ago announced a terminal in Hamburg in Germany. All these projects will be developed and will receive our ammonia from NEOM. So hydrogen for mobility is our primary destiny and our products. We're not excluding industrial customers, but to accelerate the energy transition for the world, we believe we have to break that chicken and egg problem for the mobility sector. And hydrogen for buses and trucks and beyond is the solution of the future. We have decades of hydrogen production and distribution experience, which will really change, or is a game changer when working with customers. We are developing the global infrastructure to support our customers, and we provide safer, more reliable and cost-effective solutions. You always have to understand that hydrogen and ammonia are not inherently safe. They are safe because we make it safe. We are also walking the talk. While we are waiting or developing together with our customers their transition into a hydrogen-based system, we are ourselves one of the largest trucking companies in the world. We are in more than 2,000 heavy-duty trucks around the world to deliver our products, our industrial gases. And we have committed to convert this fleet by 2030 to fuel cell-powered, hydrogen-powered vehicles. We're working on the first conversions, and the demonstration is in operation soon. To sum it all up, we're talking about building the hydrogen infrastructure. Air Products is doing that, has been doing that for decades. But of course, now it's getting more important for the world in terms of the low carbon hydrogen. We are the global hydrogen leader. We have the expertise and investment to span the full supply chain. We are now in a first mover position for large scale carbon free hydrogen, as we've proven with our project that we are working on. And we are partnering with our customers on their sustainability journey to want to be the provider for choice for green, blue and green hydrogen solution to address the significant challenges on the energy and environmental transition. Thank you very much.
So our third speaker is Richard Day. Mr. Richard, he is the Director of Strategy, Policy and Communication Growth and Low Carbon Division Department for Energy and Mining Government of South Australia. He joined the South Australian government in 2001. He is spearheading the development of South Australian Hydrogen Roadmap, Hydrogen Action Plan, Hydrogen Export Modeling Tool, and he is overseeing the development of the state's electrical vehicle action plan. So, Richard, the presentation is titled Southern Australia Clean Energy Transformation and Hydrogen Journey. Richard, the floor is yours.
Thank you very much. Good day to everyone. Thank you very much for the opportunity to present to you today. So I'll be really presenting, I suppose, South Australia as a bit of a case study, if you like, as an Australian state or territory. We're one of 8, and we very much, I suppose, you know, obviously Australia is one of many regions of the world that's really seeing it as sort of the opportunity to be a major producer and exporter of clean hydrogen. So that's certainly the sort of the perspective that I'll be coming from today. So just a little bit. Sometimes people from other parts of the world aren't always sure which bit of Australia South Australia means. So we are the the area, as I said, the state that's shaded in the bottom there. So we're around 1 million square kilometres of land. We share borders with all the other mainland states. We're a pretty small population, so less than 2 million people in a sort of a single capital city of Adelaide. So big state, small population. And I guess in terms of latitude, if you were to flip us into the northern hemisphere, sort of where Adelaide is sort of on the same sort of latitude as Cyprus in the northern hemisphere, and then the border with the Northern Territory would be, I guess, as far south as Luxor in Egypt. And I guess really, for me, it's hard to talk about hydrogen without talking about clean energy transformation. So I'll sort of. So my talk today will really sort of talk a bit about, South Australia's journey, particularly around electricity, but then what we've been doing in hydrogen and where we sort of see things heading in the future. Probably worth acknowledging South Australia. We've got very blessed with sort of a confluence of world-class wind and solar resources, and so what the map's showing you there is sort of 3 grades of solar resource across Australia, with the area in bright yellow being sort of the best irradiance, the second tier being that light yellow, and then the third tier being in the grey, and then areas that are suitable for wind generation with those above 7.3 metres per second average wind speed in blue, and where those areas of great or strong wind and strong solar resource overlap, we've coloured them in green. And I guess you can see, strong large areas of land in South Australia with that coincidental wind and solar. A little bit the same in Western Australia, and a lesser extent in North Queensland. So this was a quote from former director of energy within Tesla. So South Australia is a window to the future for energy system transformation. So I guess, so why is that? Well, if you claim to fame number 1, I suppose, is really around the sort of the speed and pace of South Australia's transformation to renewable electricity. So what you're seeing in the chart there is the amount of electricity generated every month in South Australia from 1999 to this year, and it's broken down by the generation source. So coal-fired generation is shown in black, the gas-fired generation in orange, imports for our neighbouring state of Victoria to the east are in purple, and then wind in green and solar in yellow. And you can see, sort of traditionally, we were very much a coal, gas, and a generator and a net importer of power. Over the course of the sort of the first part of this millennium, we saw steady growth in wind, in large-scale wind farms, in rooftop solar and utility-scale solar. In 2016, our last coal-fired power station exited the system, and I suppose today we're very much a wind, solar, gas state and a net exporter of power. And I guess we've been, setting new records along the way. With sort of in December last year, for that particular month, we were 79% renewable energy generation, and across the last 12 months, we've been around 68%. I guess one of the other interesting things about South Australia, and similar to many of the other Australian states, we've seen very strong uptake in rooftop solar PV. So it's sort of, if you like, the rise of the prosumer, to the point now where South Australia's sort of rooftop solar fleet is now bigger than average state demand. Over sort of 300,000 customers, around 40% of homes, on an average over 1 in 3 customers across homes and businesses. And we're starting to see similar sort of uptake charts in terms of home batteries. So yeah, quite one of the world's, I suppose, most distributed electricity systems. And then probably the third and final, I guess, key point of interest is really the successful integration of that world-leading share of variable renewables. So we don't have any hydro generation here. There's no nuclear. As I said, we've exited coal. So very much wind, solar, and gas is traditionally, well, was kind of where we're at now. So this chart's showing the amount of, if you like, the electricity generation profile over a week in October of this year, so about a month ago. Again, solar's in yellow, wind's in green, different types of gas generation are in those sort of orangey beige colours, imports in purple. And you can start to see the little blue crests on some of those peaks is when batteries are discharging, so be it big batteries or home batteries. So, and I guess it sort of illustrates, I suppose a very dynamic system in South Australia that can go from sort of at sometimes almost 100% wind or over 100% wind to 100% solar to almost 100% reliant on imports and gas. So it really shows sort of the extremes in our system. And I've highlighted there the Sunday in 16th of October where we sort of set new records. So the first of those was the minimum demand record for the state. So if you can subtract the bright yellow, if you can imagine a line between that and the slightly mustardy or the darker colour yellow, that's really net demand for centralised generation. And so what happened around the middle of the day on the 16th of October was that demand reached as low as 100 megawatts, which was a sort of a minimum demand record for our state. And we also set a record at the same time for around 116% of state demand coming from solar. And just, I guess, for a point of comparison, our record for wind is 145% of state demand. And I guess as we are expecting rooftop solar is continuing to grow in the state. We're seeing continued interest in wind and solar. And I guess you can imagine some of the key challenges we are starting to face is essentially too much solar in the middle of the day, and then other times really needing firming sources of generation. So that's, I guess, one of the key reasons. I guess we're particularly excited and have a sense of urgency around hydrogen, with those electrolyzers being available to sponge up solar in the middle of the day, being able to utilise, utility scale wind and solar projects, and looking at sort of hydrogen-based generation as a source of firm power, if you like, being used as long duration energy storage. So more on that shortly. So we're sort of neck on neck with Denmark in terms of that percentage share of variable renewables. And I guess just to round out that, in terms of that successful integration, I think there's probably 4 kind of technologies that have been particularly key. I think grid scale batteries have been key. The picture there is of the Hornsdale Power Reserve, which is sort of the famous Tesla Neo-N big battery, not to be confused with the Neo-M. So that was the world's first 100 megawatt battery, sort of held that record for around 2.5 years. Since been upgraded in size, that battery, to 150 megawatts, and is now in a first for Tesla being used to provide synthetic inertia or virtual machine mode to sort of provide a synthetic or software-based form of inertia as distinct from real inertia. Home batteries and VPPs have been really key. Synchronous condensers have been very key to providing system strength and an inertia into our system to sort of replicate the sorts of power system services that other large spinning generators would provide, and fast gas, so where speed, and you can imagine the ramp rate in the evening for us as our solar's dropping off and the gas fleet needs to ramp up quickly. Speed becomes more important at that point than overall efficiency. So where to from here? So we're on track for net 100% renewables by 2028, and so we're certainly now looking beyond 100% renewables. Certainly, this is a bit of a Sankey diagram, and I will say I'm happy to make these charts available to the organisers. So the point of this one is, you know, this is Australia's sort of energy flows. I guess the key takeaways here is, you know, we're big importers of oil. We're big exporters of coal and natural gas. And in terms of our domestic use, which is the sort of the lines circled there in the red, electricity is certainly only part of the story. So there's a lot of transition still to go. I think this probably aligns pretty well with sort of Greg and Wolfgang's point is, you know, really the future looks like, you know, green electrons and green molecules going forward. And we certainly see that sort of electrification and, if I can use the term, hydrogenification can really underpin the complete decarbonisation of our economy and ultimately lead to low carbon exports. So what are we, I guess, quick overview, we are obviously pushing into EVs. So, you know, there's, it's worth it in terms of electrification as a state. You know, we're focused on rolling out statewide charging networks, looking at trying to get the settings right on when and where people charge their vehicles. There's incentives to purchase EVs and working with fleet owners. So there's certainly a key focus on EVs, but also a very strong focus on hydrogen. And I guess I'm borrowing here from Michael Liebreich, who's the founder of New Energy Finance, Bloomberg New Energy Finance. And this is, I guess, an analogy that he's developed around hydrogen as a Swiss Army knife. It can do many different things. But I guess the key analogy of the Swiss Army knife is you don't always use the Swiss Army knife to do the job because there's other tools that can do it better. Now, whether or not you agree with Michael's assessment here, I guess it's a useful framework for thinking about those different uses of hydrogen. And I guess what he's done here is he's taken the European Energy Efficiency Rating label and then graded those different use cases of hydrogen. So those higher up is where there's sort of no real alternative, and I guess that's particularly when hydrogen's being used for chemistry, and further down, where in his view he believes hydrogen will be uncompetitive against electricity and batteries. Obviously, and as you get into the middle, greater degrees of uncertainty. So whether you agree with all his assessments or not, I don't think it really matters. But I think it's a useful way to sort of acknowledge that, you know, going forward, the world's going to be reliant on green electrons and green molecules. So in terms of South Australia's hydrogen journey, we sort of started back in 2017 with a green hydrogen study and a roadmap. We had a change of government in 2018 at the state level, and really pleased to see sort of really strong bipartisan support through the release of an action plan in 2019. In 2020, we completed a hydrogen export modelling tool and prospectus, which was underpinned by a sort of a major pre-feasibility study, which I'll show some of the key findings from that just in a moment. In last year, we worked closely with the Port of Rotterdam to look at the feasibility of a South Australia to Europe hydrogen supply chain, and that, I guess, it really proved that distance is not a barrier. That was our hypothesis going in, is that the shipping distance would render us uncompetitive. But as I guess this and other studies have shown, the cost component of the shipping cost to deliver the product over the seas is a pretty small total percentage of the total delivered price. So you can more than make up for that locational disadvantage through improved capacity factors from high quality wind and solar resources. And then we had a change of government at the state level this year, and the new Labor state government has brought in a very significant hydrogen commitment, which I'll outline shortly as well, which is its hydrogen jobs plan. So with a sort of hydrogen export modelling tool, it was a bottom-up pre-feasibility study of sort of the scale, the locations, the volumes, and ultimately the pricing that could be achieved through exporting green or blue hydrogen from South Australia, and either as liquid hydrogen, ammonia, or methyl cyclohexane. So looked at three different carriers, and really there's a lot of very detailed analysis across the whole supply chain. But really, I guess it came up with a number of port locations where hydrogen export was prospective and feasible. It also came up with some estimates there of sort of free on board pricing. So again, green and blue, and across the three different carriers of liquid hydrogen, ammonia, and methyl cyclohexane. You can see there some of the estimated, and these were, let's bear in mind, a couple of years ago now. So around $2.50 Australian or $1.66 US production cost for blue hydrogen, around $3.50 or $2.33 US for green hydrogen, and that was based in a 2030 timeframe. And as you can see on this scale there, the production costs were typically around, in consistence with what the other speakers have said, around half the price by the time you need to convert or you process, convert the hydrogen into liquid or ammonia or MCH and put it onto a vessel. So as a state, and like many of the other Australian state governments and the Commonwealth Government, have been providing funding support to a range of projects. So there's a range of different projects here, certainly not quite yet of the scale of the NEOM project, but we've certainly got a lot of large scale projects here. We're starting to push into the hundreds of megawatts in terms of electrolysis there. We've also got multiple hubs under development, so at a number of our port locations around the state. And then perhaps as a government, and this is where I might spend just a few moments, is, as I mentioned, the newly elected state government has a very significant hydrogen commitment, which is their Hydrogen Jobs Plan, and it's really a central pillar of both their energy decarbonisation and economic policy, and it's in round terms a $600 million Australian commitment to build a 250 megawatt electrolyser to provide hydrogen to fuel a 200 megawatt power station run entirely on hydrogen, and with the requisite amount of hydrogen storage in between. And so it's deliberately ambitious. It's got a time frame for delivery target of the end of 2025. But there's really two key drivers. So one is to accelerate the hydrogen industry, capture the first mover advantage within Australia around supply chain, service hubs for supply chain and the creation of new jobs. But secondly, and this is, I suppose, building on the chart I showed before with the load profile in South Australia, it's really to help sponge up that solar that we're seeing in the middle of the day, and reduce the need to curtail rooftop solar, which obviously has poor outcomes for customers, but also provide a new source of zero carbon firm power. And the idea is that the government will contract that out to renewable energy providers to firm up their portfolios and ultimately provide lower cost electricity contracts to industrial customers in the state. So that project is underway. There's been the delivery team's been established. There's been site selection analysis. There's been a market sounding from May to July this year, and we are expecting the tender processes to commence later in the next few weeks ahead of Christmas. Another project that the state government's leading is a Port Bonython hydrogen hub. So this is a port location that's currently used as a hydrocarbon export facility, as well as a diesel import facility. So we have a Santos, a company here exporting naphtha, crude, propane and butane. It's a state government-owned site with a state government-owned jetty, and through an EOI process, we've shortlisted a range of companies you see listed there that are interested in developing very large-scale hydrogen, green and blue hydrogen export projects from that location. So very excited about that particular project. And in connection with both of those two projects is the business case for a new desalination plant. So we are a dry, arid state in South Australia, and sort of new sources of industrial water are going to be quite key to unlocking sort of further growth in our mining sector as well as our hydrogen sector. And something that we've just started consulting on is some new dedicated hydrogen legislation. And so we're certainly seeing that the legislative framework that we've had to date has done a great job at developing 100, 200, 300 megawatt wind and solar farms on privately owned, typically farmland. But we're now seeing, we're fielding significant interest in gigawatt scale renewable energy projects in our more arid regions of the state, as well as offshore wind. And so, and particularly to produce electricity to generate hydrogen. And so with all the infrastructure requirements that might go around new transmission lines and pipelines and desalination plants and hydrogen plants and ammonia plants, we think that we need a new fit for purpose legislative framework that will allow us to competitively tender out public land particularly for wind and solar farms, as well as have a sort of a one window to government for all the different regulatory aspects that are associated with these sorts of projects. So we think that within an Australian context, this will be a national leading legislative framework. So that's certainly one that is a key priority and focus for us at the moment. So really, I guess, yeah, as I said, we're 68% renewables now, on track for net 100 by 2028, and we're certainly seeing opportunities to grow that to whether it be 500% or more in order to decarbonise our economy and also capture the renewable energy export opportunities that are presenting itself. So what I might leave it there, I think, and yeah, we'll throw that open, throw that back to the main meeting room to facilitate the Q&A.
Thank you, Richard, for your presentation. So I guess we can start now with some questions. So maybe I will start. I have one question for you, Greg. What is the role of the public-private partnership, in the US, especially, to address the challenges, especially associated with the development of the initial network for a hydrogen infrastructure?
Well, in the US, we've been rather slow on this, certainly far behind the progress in South Australia. That being said, we've just recently had, as part of some broader legislation, some significant support from the US federal government in terms of developing hydrogen hubs. Different parts of the regions are putting together, of the country are putting together different proposals for hydrogen hubs and all around the United States, kind of bidding for government investment support. So that's really the first time that we've had that beyond some basic research that the US federal government has done. So if you'd asked me the question 3 months ago, I would have said not much. But over the last couple of months, we've been getting quite a bit of support. And there's also, in addition to providing support to develop the hydrogen hubs, there are actually tax credits that vary depending on the carbon intensity of the hydrogen, so which would help significantly improve the economics of low carbon or zero carbon hydrogen plants.
Take a question from the audience.
Thanks for your presentation. It's very nice. And I have a question for Mr. Wolfgang. And for hydrogen transportation, as I know, so can we use natural gas pipeline to transport hydrogen? And I have also checked the data on the energy density of natural gas pipeline and hydrogen pipeline, and I found that the energy density of hydrogen pipeline is much higher than the natural gas pipeline. And could you? I would like to know if you know the reason. Thank you.
So if I rephrase your question, the question is if existing pipeline network, which is largely based on natural gas, can be repurposed for hydrogen. Very good question, thank you. We see that already happening in Europe, that big pipeline companies like Snam are starting to blend hydrogen. And there's multiple reasons to do that. One reason is to transport hydrogen. So they inject hydrogen on one side and then they take it out on the other side with means of a PSA. Of course, that is an energy intense process also, but you can do it. So you can put in hydrogen in a small concentration and take it out and on the other side of the pipeline. But there's also what they call blending. And I think in particular, the all established natural gas pipeline industry is looking into that, because there will be a way that 5%, 10% increasing hydrogen is injected into the natural gas, giving the end customer, in particular for the heating, for burning the natural gas, a higher sustainability rating over time. So you always get less and less carbon in your pipeline while the heating value goes up even. So technically there's no problem that we see at the moment in doing so. In principle, for a company like Air Products, this is just another means of transporting hydrogen, either way by putting it in, putting it out, or by blending it. We are not judgmental on how the customers want to do this. So we're working with companies doing that, yes.
Okay, thank you. I have the second question is, I have checked the data in Great Model, and I found that the energy density, that means pipeline, if we use a hydrogen pipeline to transport hydrogen, and it will consume more energy than natural gas pipeline. So I don't know the difference between the two kinds of pipeline. Could you explain this part? Thank you.
I'm not a technical expert in compression, and I guess that's exactly where you're looking at. Pipelines need compression to have it come on a certain pressure going in, and then you need the compression station to keep that pressure. And probably you're alluding to that we need more energy to compress hydrogen, which probably is true. I agree with you being a process engineer, but again, not a compression specialist. At the end of the day, I think Greg had a nice slide on this. You will always lose energy during the process of converting your energy and moving your energy around. And that is true for the fossil-based fuel system as well. So you're also refining, you're also transporting molecules. So this is just different than before, and we have to still optimize and find the most optimized way of doing it. And as always, the world needs diverse solutions, so we need it all, I guess. Greg, maybe you, from a technical point of view, want to add on that?
I'm probably less technically qualified than you are, Wolfgang, to answer that question. I think it is important, though, and I think the chart that I had, which I think is important, is looking at the complete, kind of chain and what's the energy consumption, or what is the conversion losses associated with that. I think we're going to start to see more of those, and it's going to be specific to different to different value chains, whether you're talking about, moving hydrogen or hydrogen-derived compounds from South Australia to Japan, or from North Africa to Europe. There's going to be different modes of transport and different energy consumption or conversion loss associated with each one of those.
I might be able to add something there. So in our largest electrolyzer project that's operating in South Australia is essentially a power to gas demonstration project that's been run by our gas network utility. So it's a 1.25 megawatt project, and the hydrogen coming from that electrolyzer has been blended and injected into their gas distribution network at that 5% blend. And the pipe network in Adelaide's has already been converted to sort of this modern, more plastic pipeline. So the pipes themselves are compatible with or potentially 100% hydrogen. At this stage, it's just been used at a 5% blend. And at those sort of 5% blends, you don't need to do anything different with the natural gas appliances. If there will be a threshold at which above which you would need to change the burners on those appliances to make them compatible. There's lots of different testing going on to work out what that number is, whether it's 20, 25% or somewhere in that range. But essentially, to flip to a 100% hydrogen network, people would need to change the burners on the appliances. And I think because of the volumetric density of hydrogen is lower than methane, I know for the particular demonstration project here is that they've had to change the conversion factor as it's going through the billing meter, the gas meter. So that's something that that might go in part way to answering your question about the difference in volumetric density between hydrogen and methane.
Okay, thank you very much.
Good questions from here, people attending. Yes, go ahead.
So thanks for the nice presentations. And since the topic of the seminar today is infrastructure, I'd like to ask you, okay, we have certain technologies that can be used for the production of the hydrogen, but the most probably challenging things that infrastructure for the using of the hydrogen by the population. Can you just highlight which bottlenecks we still need to solve, like taking into account the hydrogen that is small molecule, so that can be really proved of leakage. So I mean that's new materials for the construction of the engines and sealing, etc. And I'm not talking about that the stainless steel. Some steels cannot withstand hydrogen at a high pressure and temperature as well. Can you just comment what are the side problems we still have to solve to implement hydrogen as a natural gas worldwide? Yeah, thanks.
I can take a first pass on this. Just to share a story, when I started the NEOM Green Hydrogen project, I was, of course, very excited about hydrogen and was immediately looking into buying a hydrogen car myself, just to find out that there are limited fueling stations available in my area. So that was not an option for me as a customer. And I think this very much represents, in particular, if we're talking about the end user, the situation that we have in the market. Without the molecules available, we will not have solutions for users available because nobody buys that thing. There's a lot of things to be said about capitalism in general, but capitalism is in particular good in one thing: innovating at the customer side, at the consumption side. So when consumers want something and have the ability to get something, there will be a lot of innovation. Look at our electronic gadgets and everything that we have. This is all due to the strong incentive to innovate at the consumer side. So if we as policymakers, as research and as industry provide the ability to have the molecules, then the industry on the consumer side will pick up very quickly to provide the solutions for the customers. So in our products, we are set to break this chicken and egg game. We are delivering molecules in volume and trust in the market to make sure that the end user solutions will be available.
Okay, any more questions from here? Yeah, go ahead.
Hello, thank you so much for your presentation. My question is closely tied to his question on infrastructure, building transporter infrastructure for hydrogen hub. I read on McKinsey's last report, their recent report, that only 12% of the proposals on hydrogen production, the giga projects, have reached a final destination in 2022. So do you think at the current phase, we will be able to reach 2050 And is it difficult to source investments on hydrogen production?
Your question to any one of the speakers or to everyone?
No, to everyone.
To everyone. So anyone can answer?
Yeah, perhaps I will go on, Greg. I can see.
No, I was just asking if you could rephrase, if you could repeat the question. I didn't quite get it all.
Yeah. My question is related to financing the project of hydrogen production and building transborder infrastructure. So I read on McKinsey report that only 12% of the giga projects in 2022 have reached final destination, final investment decisions. And I guess the phase is very slow as compared to what is achievable. So do you think at the current phase, we will be able to build all this transborder infrastructure by 2050?
I think perhaps if I can speak from an Australian perspective, we're certainly seeing, I mean, a lot of the interest in projects is very much supply led. Now, whether it's blue or green hydrogen, it's, you know, there's a lot of interest in producing the hydrogen. I think the challenges are, you know, sort of obviously well known. Storing, moving hydrogen at scale, particularly overseas, is challenging. Liquid hydrogen's very new in terms of moving it over the ocean. It's been, you know, produced and used on land before, but moving it over the ocean is very new. Ammonia is obviously widely shipped, but I think really it's trying to obviously a lot of talk about developing up new markets, and whilst fuel cells are relatively mature technology, hydrogen turbines, hydrogen engines are all sort of busily under development at the moment. So we know Japan's been innovating in direct use of ammonia in coal-fired power stations, for example. But I think there's still a lot of links in those chains and they're quite complex supply chains to get all those things to line up and then have a bankable project. We're still at sort of the nascency of this industry. And so I think that sort of perhaps goes some way to explaining those sort of McKinsey stats of, you know, 12% of the projects currently on the books have sort of hit that final investment decision. And I guess that's one of the reasons the South Australian state government here is sort of, as a state government's really intervened hard into the market to try and get that sort of first really sizable project up in Australia to help them pave the way for all the other projects that are being worked on.
So I guess we'll take questions from the people who are attending online. So this may be this question to you, Richard. Hydrogen storage is a major challenge. So does South Australia have the required natural geology to store hydrogen at reasonable cost?
So great question. Short answer is no. So I think we're very much looking at a pipeline sort of storage solution, and we're quite interested. I mean, we've sort of seen this. I think Wolfgang alluded to it in Europe. With, you know, for example, we know through our work with the Port of Rotterdam that the port's been very focused on developing the hydrogen backbone, if you like, the transmission pipeline through the port, a sort of 45-kilometre long pipeline, and then another consortium has then been working on the transmission pipeline from Rotterdam into Western Germany. So we certainly see pipelines as a key sort of enabler for both being able to, you know, create the backbone infrastructure, but also provide that that storage option there as well.
Okay. Another question from our online attendees. This is to Greg. How ready is the U.S. for the how ready is the U.S. for the hydrogen economy in terms of import, export of hydrogen and distribution within the country?
Yeah, I would say at the moment, not very ready at all. But again, I think we've seen a dramatic change in the last year, both in terms of companies interested in investing, particularly in hydrogen production. I think as Richard Wolfgang had said as well, what we need is the end use markets develop more, and we're starting. And one of the ways that we're going to, I think, start to see that is where the U.S. federal government has stepped in very recently with incentives that, for example, that South Australia did a number of years ago. And so we're quite a bit behind, but there's an acknowledgement now that this is an important area for the U.S. The U.S. is now effectively a net energy exporter. And to the extent that we want to maintain that part of our economy, it's going to be important that we are able to participate in the hydrogen economy, and particularly eventually be a hydrogen exporter as well. And that's a particular interest to those of us in Houston, where so much of our economy is based on export of petroleum products, chemical products, and even crude oil and natural gas nowadays. As fossil fuels decline, we need to, basically ramp up another industry to replace that. So not very ready now, but a lot of attention on it.
Okay. So another question is to Wolfgang. What is the cost of hydrogen at manufacturing unit? At the manufacturing unit and after shipping, compared to the current fossil fuels?
And sorry, I really have to disappoint you on this, because as an industry player, we don't comment on cost and pricing. So we don't do that. Just to give you an idea, the numbers that people are using are very much misleading, because you never, or most of the cases, you don't know exactly what they are looking at. So we'll have very low numbers, but if you look in the details, then this is the number battery limit around an electrolyzer. It doesn't consider the power production. It doesn't consider any processing step after it, a distribution step. So hydrogen is, as we speak today, not competitive with fossil fuels, and will never be competitive with fossil fuels if policymakers don't do the needful on making sure that carbon dioxide is taxed, or other means of motivating people to change, because fossil fuel based is a fully amortized investment. So you have everything is paid off. It has been subsidized over decades now. You can't compete with a new energy form with that. One more comment to the crazy ideas how cheap electrolyzers will be in the future. Yeah, if you're looking about 20 years, maybe. If you're looking about 30 years, possibly. If you're looking about 40 years, for sure. But at the moment, and we are working very closely with the market, prices are going up and not down, and that has to do with the precious metals that is used in electrolyzers. And if you do the math and see how many electrolyzers we need in the world and what is the availability of that material, it's unlikely that it will repeat the solar industry and immediately get super cheap. And solar did that over decades too. I mean, how many decades solar was developed? I think in the 70s, 80s, and how long did it take until it got cheap? 50 years. So don't be overexcited about cheap energy. Be overly excited about low carbon energy that will do the needful for the energy transition.
Okay. I have a question. Public acceptance is essential for program expansion and scale up. What are the current plans for raising public awareness and understanding of the hydrogen infrastructure? I mean, if we talk, for example, in the US context, or in the European or Australian. So anyone can answer.
I can start off if you like. So we've certainly with the power to gas demonstration project that I gave the example of before, that was the first hydrogen production facility built in South Australia. It's currently the largest operating in Australia, and the company behind that did a very good job at engaging with the local community and the customers. And obviously, 5% hydrogen in the gas network is fairly benign. Is a fairly small production facility. So, but they certainly went at great pains to explain that the customers weren't going to see any difference on their bill. They didn't have to change their gas appliances, and they'd have no difference in experience. And that has had good feedback from the community. I've participated in other community engagement sessions around much larger projects. So, for example, a 440 megawatt electrolyzer with a green ammonia project as part of adjacent to a smelter as part of an industrial town. That has also had sort of really strong community support for it. But yes, starting to get questions about ammonia and the safety aspects around that, as well as desal and other potential. There's a small desalination plant associated with that project and brine discharges. But I think, for us, certainly in government, social license is very, top of mind, and particularly with sort of the scale of structure that's been talked about when we start talking about gigawatt scale wind, solar, electrolyzers, ammonia plants, desalination plants, pipelines and transmission lines. That's a key question for us.
Okay. Any additional comments or?
Okay, so one more question here is that how the type and size of market going to affect the type of hydrogen infrastructure? If you look, for example, like urban areas versus rural areas versus transporting, hydrogen cross borders.
I can talk specifically about, for example, there's envisioned quite a number of large hubs in the U.S. Some of those are in urban areas. For example, in Houston, we're looking at, because we of course already have existing hydrogen infrastructure associated with the refineries and the chemical plants in the area, but we're also, because we have that infrastructure, we're looking at things like heavy duty truck refueling of hydrogen. I have a student who's been working on a project associated with doing that around the trucks that operate in the port of Houston. So I think in places where there is already existing industrial activity, and in some cases like Houston, existing hydrogen infrastructure, we're probably going to start to see that first in those kind of areas.
Good. So I think it has been really a great afternoon discussion. So I would like to thank the speakers once again for your time and efforts in creating and making the presentation. I would like also to thank our in-person audience and those who are joining us online for attending today, the communication and the admin CCR team and the ICAST IT support. So at this time, I would like to close the session. Thank you once again. Thank you very much.
Thank you.